things that we do here at the Museum of Discovery, and I'm going to show them to you. The very first thing I'm going to show you is the coolest thing you've ever seen. I would even go so far as to say that I'm about to show you the coolest thing you will ever see in your entire life. Now, that being said, what I'm about to show you is dangerous. So I've got a few things here to protect myself. I've got my safety goggles to protect my eyes. I've got my gloves to protect my hands. And what if I told you that this dangerous thing that I'm about to show you surrounds you every day? It's all around you in the air that you breathe. But in the air, it's in its gas form. You guys have probably talked a little bit about the different states of matter, solids, liquids, and gases. When you get a gas really cold, it condenses down and becomes a liquid. Well, in its liquid form, this gas is negative 321 degrees Fahrenheit. That's why this is extremely dangerous. Now, you've got an important part to play here. As I pull this off, I want everybody to go, ooh. Are you ready? Here we go. 1, 2, 3. Ooh. Look at that. Look at the fog coming off of there. This is so cold that it's causing the moisture in the air around it to condense and turn into fog. Look at that. Now, this is going to look like water. It's a clear liquid, but I promise you what we have inside of this dewar is not water. This is liquid nitrogen. That's right. That gas that we were talking about that's in our air is called nitrogen. Have you ever seen water act like this? Well, maybe you have. If you put water into a pot and put it on the stove and get it really, really hot, it boils. Now, if something needs to be hot to boil, how can something that I just told you is negative 321 degrees be boiling? Well, the air in this room and the temperature of this beaker that we poured it in is so much higher than the temperature of that liquid nitrogen. So it's actually causing it to boil. All right. Now, in science and in the medical field, they use this for a lot of very important things. They use it to cool the magnets in MRI machines. They use it to burn off warts. But here at the Museum of Discovery, we just like to put things in it and see what happens. So I've got a few things I want to show you. This is a rubber band. Now, everyone's familiar with a rubber band. We talk about solids, liquids, and gases. Would this be a solid, a liquid, or a gas? Well, it keeps its shape, right? Therefore, we would call this a solid. But most solids won't do this. So this is kind of a special case. This is what we call a polymer. It's got molecules that are bound together in a way that they can stretch and move and line up with one another. And that's what makes it useful. Now we're going to put this inside of our liquid nitrogen and see what happens. Kind of bubbles, it fizzes, it causes that liquid nitrogen to boil even more. Put a second one in, just like that. Now, only a few seconds. We can reach inside and pull them out. Watch what happens now. What happened to our rubber band? It's not so stretchy anymore, is it? It got really, really cold. And when you get cold, you might hold yourself tight or huddle up with your friends to try to stay warm. That's what the molecules inside this rubber band do as well. They hold on really tight and they become brittle. But after just a few moments, they warm back up again and become stretchy. Let's watch that one more time. Wow. It just falls into pieces. But after just a few seconds, it starts to warm back up and become stretchy again. Pretty cool, huh? Now, I've got another polymer, but this one is a little bit different. Like our rubber band, it too is stretchy. But this one's different because we can put something inside of this. This is a balloon. And into a balloon, we could put a liquid, but today we're going to put a gas. We're going to put some air inside of here. You've probably seen those people who take these balloons and twist them up and make all different kinds of animals. So today, I'm going to make my favorite, the classic balloon dog. Fido. Look at him. He's very well behaved, very well trained. Fido, sit up. Good boy. You put him like this and you say, Fido, stay. He'll stay like that forever. Very well trained. He's a very good swimmer. I'd love to be able to show you some of the tricks that he can do when he's swimming. Unfortunately, we don't have a swimming pool here at the Museum of Discovery. All we have is this big beaker of liquid nitrogen. Do you think we should put him inside and see what happens? I don't know. Do you think he might pop? Possible. Let's see. All the way down inside he goes. I can hear some crackling sound, but I didn't hear him pop. Very, very strange. How could that balloon animal fit all the way down inside of that beaker without popping and letting all of the air out? Huh? Let's make another and try again. Now, it's hard enough to believe that one could fit inside of there. Two certainly should not fit. But you should never go swimming alone. You should always have a buddy. So we're going to put you down inside. Here you go. Ready? Head first. Hmm. Very interesting. Again, crackling sounds as they go in, but I didn't hear them pop. Do you think that they popped and we just didn't hear it and the air came out somehow? Or maybe they didn't pop, but the air was able to escape some other way? Or is it possible that the air is still inside of those balloons? Remember when we were talking about liquid nitrogen being a gas around us? And when gases get cold, they shrink down, they condense and become a liquid. Well, inside of our balloons right now, we have liquid air. I know, right? And I can prove to you that it's still in there. All we have to do is take them out. Just like our rubber band, we allow them to warm back up. That liquid air can't stay cold enough to stay in its liquid form. So it starts to boil and expand and turn back into a gas. It takes up the space that it did before and refills our balloon. Look at that. That is really neat. Now, our first dog has been in here for a while. So there's a chance that some of that liquid air has actually turned into a solid block of air. Isn't that amazing? Let's see if he survives. It makes so many crackling noises is that the rubber of the balloon is very brittle, so cold. And it warms back up and that liquid expands back out into a gas, just like that. Give him a big round of applause. It was pretty neat. But I have to tell you, being a balloon animal veterinarian and saving these guys from that liquid nitrogen has kind of made me hungry. Uh, I haven't had lunch yet. Do you mind if I take just a quick? We can do. Okay, we're just going to take just a real quick break. I'm going to grab a snack. It'll just be just a second. It won't take us long at all. I brought these for lunch today. My Cheetos. Oh, yes. I love Cheetos, particularly the puffy kind. I don't mind the crunchy, but the puffy are my favorite. I should say, however, it's not a good idea to have a snack while you're doing a science experiment. Yeah, if you're like me and you like to talk with your hands a lot, if you're not paying attention to exactly what you're doing, you might accidentally drop something. And if I literally just said that could happen, didn't I? I said you could be talking with your hands. If you're not paying attention to what you're doing, you might accidentally drop something. And if it, well, waste of a perfectly good Cheeto, I say, because you saw what happened to those balloons and how cold our liquid nitrogen is. Do you think it would be a good idea for me to take that Cheeto out of there and put it in my mouth? Oh, I don't know. Seems like it might be a little bit dangerous, but we're going to give it a try. Here we go. A Cheeto number one. Wow. that that's really cold. And you could see how it made my breath come out all that way. Now, somebody asked me the other day, is it really important for us to wear these masks? Well, you can see how far my breath travels. That fog that you see is all that condensation and moisture from my body coming out. But let's do a little experiment. We'll have another one, but this time I'll cover my mouth, but not my nose. You can still see all that fog coming out. Mm, very cheesy. And one last, covering both my mouth and my nose. We'll see just how effective my mask is. So all of that fog has gone right up here in front of me. It didn't even come out towards the camera at all. That's why these are very, very good to be wearing right now. They work. Mm, that's cold Cheeto. Woo! Now it's very important that I let you know I did not put liquid nitrogen in my mouth. By the time I've taken that Cheeto out of there and set it down, anything that was liquid has evaporated. It's too warm in this room for liquid nitrogen to stay a liquid for very long. Mm, I am feeling energized. Much better now. I want to show you something interesting. Have you ever been to a place that has those big pits of balls like this? And you can get in and you can play around in them. I have discovered that these really aren't good for much else. They don't have a lot of weight to them, so you can't really play catch. They don't bounce very well, so they're not good for playing bouncing games with. What I have found that you can do with them, however, is put them in liquid nitrogen. Watch this. Give it a few seconds to get nice and cold. Here we go. 3, 2, 1. Oh, that was a good one. Look at that. All of those pieces. So this kind of illustrates everything that we've been talking about. The outside of that ball got really, really cold and became brittle. The molecules were holding on tight to one another. The air inside got really, really cold. It condensed down into a liquid. That left kind of a vacuum on the inside of that ball. So when we broke the outside, it imploded. It kind of crumbled in on itself and left all of these really cool little pieces. That was really neat. Now, I do have one more thing I want to show you with my liquid nitrogen, but we're going to save it for later. So I'm going to put this back inside of my doer. If we left it here, by the time we were ready for it, it would have evaporated away entirely. So we'll pour this back inside here, and we'll save it for later for our finale of finales. Because right now, I want to talk a little bit more about how we saw that air moving when we saw the moisture in it that was condensing because of our liquid nitrogen. Can't blow on that when I have my mask. Air moves in different ways. When I exhale, my air is very turbulent. It kind of goes wherever it wants to go. So if I tried to set these cups up on top of this table and I tried to blow them over with my breath, do you think I could do it? Would my air be strong enough to knock over the cups? Let's find out. Nope, not so much. Because as you saw when we were doing the Cheeto, that air kind of comes out and it goes all over the place. It's hard for me to focus it on a small enough spot that's strong enough to knock over our cups. And that is why I brought this. This is a trash can, but it's no ordinary trash can. This has been modified into a bona fide Vortex Cannon. You can see on the bottom, we put a hole right here. And on the top, we put a rubber sheet. Now, what happens is if I tap on that rubber sheet, it forces the air inside of our trash can to come out through this hole. And thanks to a gentleman by the name of Bernoulli, we know that moving air has low pressure. Well, what does that mean? Basically, since that air is moving forward, it can't push out against the air around it. So all of that higher pressure atmospheric air pushes in behind it, and you start to get this kind of a thing going on. And now we have spinning or rotating gas, a little thing we call a vortex. Sounds cool, doesn't it? Like some kind of evil space alien pirate man, like Vortex the Destroyer. Yeah. But what it does is it allows us to propel that air forward and do really neat things like this. Oh, one more. Oh, oh yes. Pretty neat, huh? But what do you think our vortex looks like? Well, watch right here. Did you see it? No? Let me do it again. Watch close. We still can't see it. Maybe that's because we can't see the air, can we? If you move your hands back and forth like this, you can feel the air around you. We can see it when it makes other things move, like our cups, but we can't see the air itself unless we add something to it. A little bit of science juice, also known as artificial fog. You see, now we can see the air just like we could see that moisture when I was breathing out with the Cheeto. We can see it moving around. So tell me, what does it look like now? Oh, some people say it looks like a ring or it looks like a circle. I've heard people say a halo. My personal favorite, it kind of looks like a donut. Now, we can't call it a donut, so we call anything that's this shape a toroid. It's anything that's donut shaped. Look at that. Now, you might be familiar with a particular vortex known as a tornado. You all know what a tornado looks like, right? Well, this is what it would look like if you took a tornado and grabbed it at the top and the bottom and twisted it around and stuck those ends together. That's what you would end up with. The whole outside edge of that ring or that halo or that donut is spinning around. The whole thing is a vortex. Now, the most common vortex you're probably familiar with would be one that you might see anytime you drain water out of your sink or out of your bathtub, spinning water as it goes down the drain. I can illustrate what that looks like using this, my handy dandy handheld vortex generator. Okay, it's not quite that fancy. It's just a couple of plastic bottles that we've stuck together, put some liquid inside, and left this one empty. Now, normally, if I wanted to get something from here to there, all I'd have to do is turn it over. Gravity would take over and it would whoosh. But as you can see, our water is not whooshing. It's barely even dripping out of that bottle. The reason for that is this bottle is not empty. It's completely filled with air. It's got a gas inside, no room for anything else. If we want this liquid to go into that bottle, that air has to go somewhere first. When we turn it over like this, the liquid tries to go down, the air tries to go up, and they get bottlenecked. Look it up. When you find out what bottleneck means, that'll be hilarious. But we can help it out because a vortex is the best way to exchange liquid and air from one place to another. If we give it a little bit of a spin, because we said it has to be rotating or spinning liquid or gas, now we have a vortex, and one that looks more familiar to what you guys would probably think of when you see a tornado. So what is happening is right up the middle of that, there is a tunnel of air, almost like a straw. It allows the air to come up right through the center while the liquid spins around the outside edges. That way they don't run into each other and they can exchange places a whole lot easier. Now, we've seen what a vortex looks like in water. We've seen what it looks like in the air with our vortex cannon. How would you like to see what a vortex looks like in fire? Right? It seems like a very strange thing to be able to create a vortex from. Now, luckily for us, this isn't something that happens here very often in the States. Sometimes when there's wildfires, if the wind is just right, it will cause those flames to spin and become a vortex of fire. All right. Now, to create ours, we're going to use this trash can. Now, it's a little different than our other trash can because this has holes in it. Because in order to create fire, you have to have a few things. One, oxygen. And this is going to allow the oxygen to get in to our flame. The second thing that you would have to have is some kind of a fuel, something to burn. In this case, we're going to use a little isopropyl alcohol. I'm going to put that right down here inside of our trash can. Very good. The last thing you have to have is a heat source or a spark. This is going to be our heat source. This is going to be our spark. So if we add this to our fuel with the oxygen that's here in the room, we can very easily create fire. The only thing that's missing is the one thing we need to create a vortex, and that is spinning. Look at that. A tornado of fire. What happens if we go the other way? Wow. Isn't that amazing? Through that rotation and the circulation of the air, we cause that plasma, that fire, to spin, to rotate, and become a fire tornado. Wow. Pretty cool. Let's hear it for the fire tornado. Wow. Kind of a terrifying thing to think about that could actually happen. I've heard stories of that happening down in places like Australia. And like I said, during the wildfires, there's always a chance of that. But all right. I told you earlier I was going to save one last thing with our liquid nitrogen. And that's a little something I like to call the finale. Hope you guys are ready. Now, in order to do our finale, we have to have just the right amount of liquid nitrogen. So we're going to use our beaker to measure it. You see, it's got numbers here on the side that we can use to see how much is inside the container. We're going to use 400 milliliters of liquid nitrogen. Gets a little difficult to see with all that fog, doesn't it? A little bit more. Perfect. 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 Now, over here on my table on the side, this whole time, I have been boiling some water. Now, boiling water is about 212 degrees Fahrenheit. We're going to combine that with our negative 321 degree liquid nitrogen. That's a difference of over 500 degrees. If we did that right here inside of this glass beaker, it would shatter. It would be too much of a temperature change. So we're going to use this just to be safe. We've got a metal pitcher here inside of our metal bucket. That's going to make sure that our liquid nitrogen stays contained. Whoop. Look at that. It froze right to the bottom of my beaker. Let me straighten my towel out again. That's how cold this is. It made it freeze solid. I love it. Whoop. All righty. 400 milliliters of negative 321 degree liquid nitrogen. The other thing we're going to need, of course, is our hot water. Listen to it popping and cracking as that metal gets cold. All right. You can see the steam coming off of our hot water, the fog coming off of our very, very cold liquid nitrogen. Here we go. Are you ready? Count down with me for the finale in 5, 4, 3, 2, 1. Isn't that amazing? It made fog. You're not impressed. I can tell. Well, maybe if we added just a little bit more hot water, what do you think? Maybe we should add the whole thing. But I tell you what, if I'm going to add the whole thing, I need everyone to count with me as loud as you can. From 5, 4, 3, 2, 1. Wow. Did you see that? Look at all of that fog that this has created. The second that we threw that hot water inside of our liquid nitrogen, it caused all of that liquid nitrogen to instantly turn back into a gas. And since it expands when it becomes a gas, it's so much bigger than what can fit inside of our pitcher. And that's what causes it to just shoot out of the top like that. That's amazing. Let's look inside and see. We've got some really cold air there, lots of fog. Sometimes we even get ice that instantly forms down in the bottom of the pitcher. Isn't that incredible? What amazing reaction. Wow. Well, I don't know about you, but I just had a great time having a ball making some really cool science happen. Hope you guys enjoyed it. Like Thomas said, we're going to take some time if you have any questions about what you saw or any of the experiments that we did today. We'd love to have you ask those questions, and we'll answer them to the best of our ability. Once again, want to thank PPG very much for sponsoring today's show, making it possible for us to come into your classrooms to show you some of our very favorite awesome science. Wow.
Let's give a big round of applause to Mr. Sean Carlock. How fun is that?
Well, thank you.
All right. I think we've got some time for a few questions. So if we could either have the teacher translate those questions or have the students come up and we'll be able to, you can unmute your mic and ask us our first question. What do we have?
The gas that you was using, was that dry ice?
So that we were using there was not dry ice. That was liquid nitrogen. Dry ice is a little bit different. That's actually hardened or essentially frozen carbon dioxide gas. It's not quite as cold as liquid nitrogen. It's only about negative 109 degrees Fahrenheit. And the reason that they call it dry ice is because it goes through an interesting process called sublimation. And we talked about how things go from gases to liquids and then they become solids. Well, in dry ice, it goes from a gas to being a solid and then goes from a solid back to being a gas. It skips over ever being liquid. And that's why they call it dry ice, because it never gets wet.
That's an excellent question. What's our second question for the morning?
I'm definitely not dry ice. I've got a little.
You can ask her. What did you go to? Did you learn all of this?
She wants to know what school you went to where you learned all of this.
I learned everything that you just saw here at the Museum of Discovery. So my background is mostly in entertainment, and when I came here and started working here, I got to learn all these amazing things, and I love it because it's still very fascinating to me. Every day I'm here, I learn something new. So the best way to learn this is just to have a creative mind, to look at something and go, why did that happen? What caused that? And then nowadays you have amazing resources. You can search things on the internet. You can go to the library and look in books and encyclopedias. Phenomenal resources to find out how all this science stuff happens. Good question.
And from my perspective, I was a history major. So even though I didn't have a science background, when I came to work at the Museum of Discovery, I, just like Sean said, started learning new things and expanded my understanding of the amazing world around us. So that's what you guys get to do in school.
Mhm.
And even in, say, your history or your reading class, you can look at things through the lens of science, which is what is the evidence showing us about how this world around us is made up. from a physics standpoint, from a chemistry standpoint. You can look at it through a lot of different lenses. So we hope that you gain an appreciation for science from seeing this show here today. What's our next question?
How did he eat that Cheeto if it was under the 300 degrees?
So, whoop, there we go. So once I pulled that Cheeto out of that negative 320-degree liquid nitrogen, the air in this room is a lot warmer than that. So instantly, if there were any actual liquid nitrogen left inside, it is evaporated, it's turned into a gas, it's left. All that's left is that really cold Cheeto. It'd be interesting to find out just how cold it is when we actually put it in our mouths. We should test that sometime. See if we can get a thermal thermometer and actually get the temperature of that. We might have to do that.
And most thermometers that go that low are rather rare and expensive. I don't know if they'd be willing to let us use it on a Cheeto.
Hey, it's for science.
That's right. That's right. That's a great question. I really like the way you're thinking about things.
Right.
And one other thing to note is that anytime we're doing a demonstration, even if it looks crazy and wild and out of control, we practice everything here over and over and over, and we talk with other scientists and museums to figure out what's the best way we can demonstrate this amazing, awesome science in the safest way possible. So everything that we do has been rehearsed, has been practiced and refined so that we're doing it in a consistently safe way. That's something really important to note because you can see some pretty wild stuff online that doesn't necessarily always follow the correct safety procedures. It's a great question. And what's our next one?
How did the liquid nitrogen get so cold?
How did the liquid white nitrogen get so cold? Because there's nowhere on this planet that liquid nitrogen can exist in its liquid form naturally. So this has to be made in a laboratory. They take a bunch of nitrogen gas, they put it under a lot of pressure and extremely low temperatures, as cold as they can get it. And then when they release that pressure, there's a very interesting thing that happens where it forces that temperature to drop even further. So if you've ever seen where they have the cans of air that you can use to clean out your computer keyboard and things, you'll notice that as you use those, the outside of that can will get really, really cold. It might even start forming frost around it because as that pressure is released, it's forcing that temperature to drop down. So that's what they do. They use a lot of pressure and cold temperatures until they can finally get it to the point that it liquefies. Then they have to store it inside of special containers so that they can keep it as cold as they can. But always this liquid nitrogen is evaporating. That's why this lid is loose so that gas can escape. If this was really, really tight on here, as that gas kept expanding, it would build up enough pressure that eventually this container would fail and explode. So that's why we say liquid nitrogen is very dangerous stuff. It absolutely can be.
Thank you guys for that question. What's our next one?
Really good questions.
How did y'all make all the fog come out of cannon, but it didn't all come out?
So to do
Like
that,
you fired it out the cannon.
you really
Some
couldn't
fog
see
is
this because it was
in.
off to the side. But this is a fog machine. So if you've ever been to a place that has theatrical fog, a haunted house or things like that, this uses a glycerin-based liquid that it basically it heats it up and causes it to come out as a fog, and it shoots out here. We catch that inside of our trash can, and then when you hit it and the air comes out, it takes the fog with it.
Does that answer what your question was on that one? Yes. All right. Perfect. Yeah, we get that one a lot, and those are decently affordable. You can get kind of an entry level fog machine for around $30 or $40, and so maybe a few classes chip in together and purchase one. I would like to say the fog machines are fantastic for doing experiments about the movement of air. So you can do a lot of things exploring that dynamic movement, which normally we don't get to see. Sometimes you see it in the fall, like when the leaves are blowing, you can kind of see those wind patterns. You can see it on water, like when wind is blowing on the water top. But fog is a great way to see it in 3 dimensions. What's our next question?
What happened if you put the liquid nitrogen inside the balloon?
inside the balloon. Did y'all get that?
And one thing y'all might want to do is if y'all can turn your volume down on your, I'm assuming like a smart board, that may help with the reverb we're hearing. So not so much that you can't hear us, but maybe while we ask the question.
Okay.
So can you ask that one again for us, please?
Ask it again.
What happens if you put the liquid nitrogen inside the balloon?
If we put the liquid nitrogen inside the room,
In the
Is that the
balloon.
question? In the balloon. Oh,
that is a good question.
wow.
Well,
That is a very
I know
good
what I
question.
think I know what would happen.
You'd have to be really, really careful because if you bumped that balloon against anything, I'm sure it would shatter into a bunch of pieces.
Yeah, and my thought would be you would really want to balance your quantities. So for example, if you were to get maybe what I'd say like a teaspoon, like a small amount of liquid nitrogen, if you got like a little teaspoon, and if you were to pour it in a balloon and then tie it off very quickly, I think that would expand. So it's going to expand over, I think it's 700 times its volume. So it's going to get a lot bigger. And
would it though? Because
I think it would.
the balloon would be so cold. I think if it tried to expand just like the rubber band, it would just break.
See, I don't think it would have enough of a cold temperature to cause the balloon to fail.
You guys ask really, really amazing questions.
And what we'll do, so for example, we wouldn't just immediately try this because we don't know what the result would be, and there could be some potential hazards that we haven't thought about. So what we would do is we would talk to experts, or we would ask other folks that have already tried this to guide us on how we could safely host an experiment on it. But that is an amazing way to think about it, and I really appreciate your question on that. What do we have for our next question?
I'm going to be thinking about that all day now.
Hey, is dry ice colder than liquid nitrogen, or they? Is dry ice colder?
Liquid nitrogen is negative 321 degrees Fahrenheit, and dry ice is, it kind of seems silly to say it's only negative 109 degrees, but it is not quite as cold as liquid nitrogen, but it's still very, very cold. You have to be careful with that. You can easily burn your skin with temperatures that are that cold. While dry ice is something that people can get much more readily than liquid nitrogen, you still want to make sure that you're taking all the precautions, knowing proper procedures and ways to handle it, gloves, and never touching it with your bare skin.
Yep, that's a great one to talk about the comparison. And there's also a difference. So dry ice is going to be in that solid form, and liquid nitrogen is still going to be in a liquid form. So it's weird to think about, even though the liquid nitrogen is in the liquid phase, it's actually colder than carbon dioxide in the solid phase. For nitrogen to go into liquid phase, it has to be, or excuse me, for nitrogen to go into the solid phase, it has to be even colder than negative 321 degrees Fahrenheit. Looks like we have time for about 2 more questions. So what are our last couple of questions for our program today?
Okay.
How did the Cheeto taste?
Fantastic.
Yep,
Now that's a test.
tasted like a delicious Cheeto. I also have had many Cheetos in my day that have been frozen with nitrogen, and they're just as good as any others.
Okay, one more.
Very refreshing.
How dangerous can the liquid hydrogen?
Is liquid nitrogen a liquid or a gas?
What?
All right, I hear 2 questions. Pamela, I can answer yours, or the one on Pamela's screen. I can answer that one quicker. So liquid nitrogen is right in the name. So it is liquid, and then it's the compound nitrogen. It's going to be an O2 molecule. So yeah, that one's going to be in that liquid phase. To turn it into a solid has to be a lot colder, but it's mostly in that gas phase. Every breath you take has gaseous nitrogen that you breathe in. And then what was our other question? I heard it from the other classroom.
How dangerous can the liquid get?
How dangerous?
How dangerous can nitrogen get?
It can be very dangerous, and for several different reasons. You know, if you were to put your bare hand into liquid nitrogen, it would freeze your fingers solid. We do a demonstration where we use a hot dog to simulate, you know, maybe somebody's finger if you accidentally put your finger in for too long. And if you hit that with a hammer, it shatters like glass into itty bitty tiny little pieces. So there's the cold of it that can be very dangerous, but also like we talked about, if we didn't have a loose lid on our dewar and it built up and it evaporated and created more gas and build up pressure, that has the potential to go boom and could be very, very dangerous.
And there's also one other danger that a lot of people don't think about, and that is ventilation. So nitrogen takes up a lot of volume as it turns into a gas. And if you don't have a well ventilated room, so say you store all your nitrogen in a smaller closet, that entire room eventually will be filled completely with nitrogen gas, which means there's no oxygen. And nitrogen is odorless and colorless. So if you were to walk into that room and shut the door, you could pass out from a lack of oxygen, and that can cause asphyxiation and even death. So nitrogen has some very severe consequences if not handled properly or stored properly. We are at our time mark. So what we can do is, for all of the students that have additional questions, if you will make sure and write all of those down, get them to your teacher, and have your teachers email Beth Nelson, and we will get our answers to you guys, because we love these questions. This was so much fun. You guys were thinking about it in some really amazing ways. It's really showing that you're thinking about the world around you, which is exactly what we want out of this program. So we really appreciate being able to connect with you guys. We're incredibly thankful for PPG for providing this opportunity for us to connect with you all. We hope that there's opportunities in the future for that. So if you have additional questions, let your teachers know, and we'll get those responses back to you. Teachers, do you have any questions or announcements you guys need to make?
No, but thank you so much. That was fun.
Yeah, thanks.
You bet. Thank you, guys. Hope y'all have a wonderful day.
Bye.